Hi guys, today we're going to continue with the electrochemistry, and remember we actually did quite a lot. You look at here, we did standard electropotentials, right? Remember it's called SEP, right? And today we're going to look at standard cell potential, SCP. The difference with it, okay? Remember, standard electropotential is very specific. It must have hydrogen electrode. These two must be there for one part of a cell. A cell contains of two half cells. So one part must be hydrogen. You've got SEP, okay? Right, now here we've described hydrogen electrode, hydrogen electrode. Now here, this is the question here. Okay, I'm going to give you the question here that actually asks you to give up here. Okay, no, here. Where am I? Okay, show you the marking scheme now here. Okay, here they ask you the question with the aid of a fully labeled diagram. Describe the standard hydrogen electrode. See now, 4 marks, normally 4 marks. Okay, now here. So you draw the diagram. Remember, this one is like a rocket, a tube, okay? Right? Don't have to put holes in this metal, okay? And this part here, okay, platinum. This is only a half cell, okay? Don't care, they only want this part here, right? H plus must be 1 mole per dm cube, okay? Temperature of 25 degrees centigrade, up to you. Okay, now the marking. H2 gas going in, that's not being produced, okay? It's just going in. H2 gas, arrow going in, that's 1 mark. Okay? Platinum electrode in contact with solution with H2 bubbling away. Okay, H2 bubbling, okay. Okay? So this whole part here is 1 mark. 1 mark here, right? H plus or HCl, H2O4, 1 mark here. Basically, best of course to put H plus here equals to 1 mole per dm cube, 1.00 mole per dm. It's the best deal. You can't put it wrong. Okay? Or HCl is 1.00 mole per dm cube. Or H2O4, 0.50 mole per dm cube. Anyone will do, but don't put nitric acid because NO3 minus is an oxidizing agent, so don't do that. See, that's why you put HCl and H2O4. I will explain that later, okay? So all the solutions, see if H2O4, okay? All the solutions are 1 molar, and this is the standard conditions. Okay, so there are 4 marks here. Fantastic, isn't it? Just on the diagram and the labeling. Okay, so this part here, as you said, they give the mark for just this describe, come up before the standard hydrogen electrode. Okay, now next one, of course, is describe the methods used to measure the standard electropotential. Okay, right? That means you have to use hydrogen electrode for all these metals with the ions, of course, like here you got copper with your copper 2 plus ions, okay? Okay, which we did already, isn't it? Now I'm going to show you the question I left out as that day. There's a time factor. Now here is the question, right? So you draw a fully labeled diagram of the equipment needed to measure the voltage, isn't it? Or they call it EMF, right? Voltage here, EMF. Okay, E voltage meaning EMF. You have to know what it means. Of electrochemical cell, it means there are 2 parts, okay? 2 parts of a cell, all right? Consisting of standard electropotential, it means hydrogen electrode, and the standard copper, okay? Which means they need to draw the whole thing. Now, to make it easier for us, I got the marking scheme here, all right? I think I got here. Let me just go, okay, here, okay? Simple as that. So you can see half a cell, half a cell, okay? So this is hydrogen electrode, same as that. H2 gas going inside here. This is the container, don't label it. As long as it's an enclosed tube, you okay, platinum, okay? Voltmeter, V. Salt bridge must be labeled. Sorry, copper here. I'm going to drink this, Copper here, Best to put copper 2 plus here equals to what? 1.00 mole per dm. Always remember this because it's 1 mark. See that? 1 mark. Here, pressure equals to what? 1 atmosphere, 1 mark. Temperature equals to what? 25 degrees centigrade. These are all standard. Okay, so you can see here, voltmeter and salt bridge, again, 1 mark. Mark number 1. Copper and copper 2 plus, okay? Copper 2 is better. Copper sulfate or copper chloride, you know, well, this is important. Okay? H2 arrow must be in. See that? Okay, into this mineral acid. All right, H plus. Okay, 1 mark. Platinum in one solution. Okay, platinum here, label platinum. See, all got 4 marks, man. Fantastic, isn't it? Now, the other 2 marks or 1 mark later you can see is given for the voltage. Okay, somebody ask you, right? Now, this, as I said, this is your standard electropotential. Okay, SCP. But sometimes they ask you for the cell potential. What's the cell potential? Can also. So this, let me just put down here. It's called standard. By right, it's called standard electropotential. Because why? You compare it with hydrogen. Okay. But they can put it around because of standard cell potential is equal to what? Standard here, cell potential. This one includes this, no? But this don't include this. Okay? Potential, they ask you. So the best way to do it is, right? After writing the whole thing here, they ask you for the poles of this cell. Now, how do you figure out the poles? And how do you, first course, how do you figure out the poles? Okay. Secondly, how do you figure out the ionic equations? I teach you today already, okay? And how do you figure out 3, the overall redox reaction? And 4th, how do you figure out the E? Now I put cell here. Okay, now let me show you very simple. First of all, you have to know that in this case, it's quite simple. It's hydrogen here and copper here. So you look at your data booklet. The data booklet tells you everything. Okay, now hydrogen. This is what? 0. Because why? It is in acid. Okay, now later you can see one is in alkaline. No, so be careful which one you choose. Okay, so if it's acid, this is 0.00. Okay, so it's neutral. See, copper. Look at copper here. Copper, there are a few, 4 in fact. Copper with copper 1 plus, copper with copper 2 plus, copper 1 plus with copper 2 plus, and so forth. So we choose the one that we have in our thing. This one, copper and copper 2 plus. So it's plus 0.34. Plus means that it's a pole name. The pole is positive, which means here I'll put now copper here is positive. Okay, so here must be negative. Right? See, so this is how you determine the poles. First of all, determine the poles. Once you determine the poles, of course, negative means what? Electrons are coming out. Source of electrons. Negative means what? Source of electrons. That means coming out. Okay, coming out here. Electrons flowing here. Flowing to here. Which means in that case here, right? If you talk about what is the chemical reaction. So now hydrogen here. Where's hydrogen? Okay. Now, I told you this is a reversible reaction, right? It means 2H plus 2E can go forward to give you H2. Now, there's no H2 inside the system, is it? Can go backwards to give you your H plus and 3. So which way is it going when you connect it with copper? Which way is going? It's negative, isn't it? Which means it's going what? If it's negative pole, it means your H2 is going to go to 2H plus the 2 electrons, which is coming out. See now? So this is the reaction that's happening now. Positive. Copper is going to take in electrons now. Copper. Here, copper. Here, copper. All right. So copper 2 plus here, copper 2 plus can plus 2 electrons to give you copper. But there's a copper there, what? Metals there. It can go to, can be oxidized to copper 2 plus and copper 2. So when you connect this system here, this half cell with the system here, what is actually happening? We say that it's positive, that means it's going to accept electrons. So which means this is going to be the direction, which means that copper 2 plus, plus 2 electron to produce copper. So there must be now a redox reaction. This, of course, is oxidation. This, of course, what? Reduction. So now, then you have the overall. These are called your half ionic equations, okay? Right? So now you get the overall full equation. So you cancel off the electrons 2 here, you get H2 plus Cu2 plus gives you 2H plus. Now this is what is actually happening. Copper get deposited. Okay. Now, so here you can put the E value here. If it's going forward here, it's 0.00 anyway. So it's going this way. Okay. So copper is going this way. Right. If it's going this way, that means that it means this way is positive. It means this one will occur. Okay. Positive means this direction will occur. Okay. This is the reduction. So you quote the positive here. Put positive. If you go backwards, you put minus. Okay. You just reverse it. So positive 0.34. Okay. So here is positive 0.34. Now this is called the EMF of the cell, or standard potential, standard electric potential. But you can put standard cell potential because it doesn't matter because it is inclusive, positive 0.34 volts. Another way to deal with this to find something is very simple. We call it E cell. Let us see, cell equals to E reduction minus E oxidation. So you must know which is reduction, which is oxidation, which you should know. And the E here, you must be original, like here. You cannot change the sign. Here you can change the sign, okay? Go forward, backwards, can change the sign. But here you can change the sign. So in this case here is equals to, reduction of course is copper. So it's plus 0.34 minus 0, same, plus 0.34 volts. So this is a very useful formula. Okay, you'll see later as I show you. Right, so now we have seen how it happens here. All right, okay, so draw a label diagram. You can see the marking scheme here. Right, there are 4 marks here. If you plus this one here, 1 mark for copper being a positive and the rich, and also one more mark. They asked 1 mark is for the direction of electron flow. That's 1 mark, which means this one is 1 mark. So 6 marks. See now, 6 marks. Easy busy. Okay, now let's go to another one. Remember, all these are on diagrams. All these are SEP, standard electric potential, but you can call it standard cell potential. Okay, hydrogen is there. Now here another one. Now here is what's very simple. X the metallic element. Draw a full label diagram. Okay, full label to show how the standard electric potential. See now. Okay, so SCP of X2 plus is not. Of course, in this case here, what you change only this part here. You put, instead of copper, you put X. Instead of something, you put X2 plus equals to what? 1.00 mole per dm cube. Okay, everything is same. Okay, direction of movement electrons all same. Easy, isn't it? Right? So it's very general. Say here, what are the conditions needed for this value to measure standard? The 3 things. Okay, remember, temperature is what? 25, or you can put 273 plus 25 is equals to 298 Kelvin. Now you want to be perfect in a sense. 1 atmosphere, and what? Concentration of ions equals to what? 1.00 mole per dm cube. There are 3. In fact, there are 4. You know, if it is not a metal electrode, you will use platinum. Platinum as neutral electrode. Okay, so sometimes they want this. Okay, but this is a carrier. So state the charge carriers that transfer current. Of course, through solutions ions. Right now. That's why through the salt bridge, this is done with the salt bridge. Salt bridge, okay? Salt bridge carry ion transfer. Wires is electrons, of course. Okay? So this is quite simple. SCP again. Now here, draw a Fourier library for to mention SCP for F2 Of course, in this case here, right, there is no metal, there's no iron there, right? So how do you do it? I told you before. Today we're going to focus on a few more of these things here. Remember that you see here, you see the here, see, right? Now this I told you this one is the metal ion immersed in Fe2 plus 1 molar. This one here is iron metal immersed in Fe3 plus 1 molar. This one here, there's no iron one. So where the electron is going to go? Okay, Fe2 plus and Fe3 plus. Now these two I must have there. I must be in the cell. So I need a platinum wire to conduct electricity. Okay, so how do we draw it? Now I think I told you yesterday. Now here is the typical one. Okay, I show you here. All right, I planned everything already, so faster for us to cover the whole thing. Okay, here, right? See, hydrogen again. Arrow must go inside. Okay, platinum. Whenever there is no metal to in the system, you put platinum. The H plus is 1.00. Okay, going down here, salt bridge. This whole thing is 1 mark. Platinum. So I must put inside here Fe2 plus 1 molar. Fe2 plus, that means that both these things, it can go either way. Fe2 plus Fe, remember Fe3 plus electron will go to Fe2 plus. Fe2 plus will lose electron, go down, so it's reversible. Okay, so see marking scheme. H2 always a good delivery system. This 1 mark. Fe2 plus, Fe3 plus label. Now I told you what labeled here, yes, but this one is better. Okay, platinum electrodes for both of them. 1 mark here. Salt bridge and 1 meter again, 1 mark here. Okay, acid, of course, this also must be labeled. 5 marks, man. My goodness, so simple, man. Okay, diagrams very important. So make yourself expert in this. Okay, of course, if you ask the voltage here, you can straight away say the voltage is equal to what? Positive. What is this? What? Positive 0.77. Okay, positive 0.77 volts. Flow electrons, this is negative. Why not? Okay, this is positive. One negative and positive because Fe2 plus is positive. Okay, so negative. So electrons will flow from here. So that would be 6 marks. Fantastic, isn't it? Very simple. So electrochemistry is very simple in the beginning stage. Of course, later you find it a bit more challenging. Now here, I'm going to go to this now here. All right, I'm going to go to the other part here. All these things are. Now this one, of course, is copper, quite simple, isn't it? Okay, so I won't go through this. It's quite simple. Okay, now I'm going to go now for this type here. All right, gas and gas. Okay, hydrogen and oxygen. This is called a fuel cell. So we're going to start on this here. Now let me go back to the original thing here. Okay, remember? So we have done metals and the ions. We've done non-metals, for example, chlorine gas with Cl minus. Okay, okay. Well, maybe I show you the one. I got one here. Chlorine gas. Okay, just to finish the thing. All right. I got one question here, which is like that. Okay, where is that fella? Okay, here we are. Okay, I think can. Okay, now this is a standard cell potential. Okay, now here, I think I'll go later. Otherwise, you get mixed up. Never mind. Okay, now let's start with this one here. As I said, okay, I'll go with the chlorine gas after. Okay, right now. So ions of the same element with different oxygen state. I done with you. Fe was Fe3 plus. Okay. Now this part here, we're going to do D and E. This part here. Okay. With half an hour more, we can finish it. No, more than half an hour, but 40 minutes more. Sorry. Calculate a standard cell SCP. Is not okay. It's SCP already. That means anything goes. Right? I can put anything. We're going to do the famous one called Daniel cell, which you done in form 4, form 5. By combining two standard electric potentials now. Okay. This is SEP. Two, combine them. Okay, so this is how to do it. You're going to use the famous Daniel cell first, okay? And then use the standard cell potentials to explain, deduce the flow of electrons in a simple cell. Okay, this one is later. We have time, we do that. We don't have time, we will do it next day. Okay, so we take it slow, right? Make sure you get the basics is very important. Because once you get the basics right, no problem. Any question, no problem. Okay, now let's go to this part here. Okay, we're going to look at your standard electric potential, but in gas form, right? Of ions of different oxidation states without any metal there. Okay, so I've got examples here ready for you. See, failing to plan is plan to fail. I don't plan to fail, so you must not plan to fail. You must always plan ahead. See, all this plan already, otherwise we cannot finish. Okay, now here is the first one here. I did all these things planned already. Now, if they ask you to draw, right, a diagram, right, for this cell, this half cell, this famous chromium, this is orange, it's a dichromate. Okay, actually potassium dichromate, K2Cr2O7. It's called potassium dichromate. Remember your Form 5, now they ban it already because say it's poisonous. Dichromate. Dichromate. Okay, famous one is orange in color, if you remember that. All right, in your organic chemistry, orange will turn, this is green color. They ask you here, no? So even though they ban it, well, they still ask in exams, okay, chromium 3, this is chromium 6, isn't it? That's chromium, see, chromium 2O7, the whole thing here is -2, right? Oxygen is -2 here, this X here. So positive, the two combined together must give you -2. So 7 times -2 is -14, 2 times S, 2X. So 2x minus 14 equals to -2. 2x is equals to what? Remember, bring over, it will be 12 positive. So x is equals to, right? Now, always in this case, oxygen state, right? Put the sign first, +6. So this positive, and here, but here you put 6 positive. Interesting, right? There you put +6, here put 6 positive. So from here, 2 of them, of course, to go to 3+, you need 6 now, okay? Because here to here is 3 electrons. Okay, one more take in except 3 electrons. So 2 moles times 2. Okay? Somebody must be giving this one. So if this is this fellow here is to go forward, so now inside here I got both of them. I got this fellow here, which is green color. I got this fellow here, which is orange color. So it's like a bit brownish black color. I put acid inside here. So there are 3 things here. See, in this half cell, guys, this is a half cell. I must include all the ionic species here. The dichromate, the acid, normally it's from H2SO4. Okay? It's excess normally. And your Cl3+, which is the green color. All of them inside here. See, 1, 2, 3. Because it can go forward or backward, depending on who is writing it. Right? Like for example, in your house, your father to you is a father, but your father to your mother is her husband, or your father to your grandfather is a son. So the role play depends on who is relating with. So it can go forward or backward depending on who is on this side of the cell. Okay, all right. Now of course it's called standard electrode potential, which means this cell must be what? Must be hydrogen. Okay, plus electric potential. Let's look at the definition again. Just not to make you see. The EMF of a cell of a test electrode, in this case, is your chromium. Okay, /H+/Cl3+, and a standard hydrogen electrode now. So it's SCP. So remember, this is what we are dealing with here, right? So if it asks you to draw like that, then draw like that. So they always ask you now, next of course is to, well, what the poles, they ask you for the poles. Okay, first they'll ask you for poles. Secondly, they ask you for the overall equation. They won't ask you for an equation, but I'll teach anyway. 3, they ask you for the EMF of the cell. They use cell, no, because cell includes standard electric potential. It means if hydrogen here is still called a cell, okay? What's the voltage here? So 3 things they ask you. Very simple. Don't worry, you should get score on. So once you get this draw diagram here is 6 marks already, right? Or 4 marks up to the examiner. So how do you figure out the pose? Very simple, right? Because why use a data booklet? Okay, chromium, right? Now this one here, right? Remember, it's always written in the reduction form. Here is always C plus electrons. It's always reduction. That's why it's called the reduction potential. This is actually called the reduction. This is called the reduction potential. Okay, in most books, they call the reduction potential or the reduction voltage, because this is written in reduction, because you can use for comparison straight away. Right? Simple, isn't it? Because you know how we derive it and so forth. Okay, so now this one here. All right. So when compared to hydrogen, hydrogen is 0. Of course, that means hydrogen is 0. It means it's 0. It means this is positive. This is it. Let's compare hydrogen. All is compared to hydrogen. So it's positive. So what here? So here is positive. And hydrogen is negative. So once you decide the poles already, you can talk about electron flow already. Negative means what? Source of electron means like flow from here. Electron. So electron will flow from here. That means here must undergo what? Oxidation. See? So remember hydrogen. Well, let me just give hydrogen again. Now hydrogen in this case here, you're not sure. You look at here, it's very simple. See? Now this is given as the equation. Right? So here hydrogen. Right? Give it as 2H plus 2E. Of course, as I said, it's really in a reduction way, H2. But doesn't matter. Now, if it's giving out electrons, that means is it going forward or going backwards? It's going backwards then, right? No, because give electrons back. So H2 must be coming 2H plus 2 electron. So now I put down here. See? H2 becoming 2H plus 2 electrons. Okay? So it's the first thing I write. It means hydrogen is becoming a H plus. It means here they will increase in H plus concentration. Don't care about that, none of our business. So I put down here 0.00. Why I'm quoting it from here, the voltage, right? Here the voltage, right? 0.00. Okay, got it? Okay. Now, next, of course, I want to write here the dichromic part. So electrons coming in. Wow, that means here is undergo what? It must be going undergo reduction. Something here must be accepting the electrons. Now, is it Cr2O7 that accept electrons or Cr3 plus accept electrons? Obviously, this one is not. You see, plus electron. I know. So this fourth is the reaction here. That means reduction is this one here. So I put down here, I just copy the thing here. Okay, Cr2O7, 2 minus plus 4H plus 6 electrons to give this one here. So these are the 2 equations that's happening. These are your half ionic equations that is happening now as I close the circuit, right? But now to write, so I put the voltage here. This is the original voltage as in the standard electric potential, okay? I don't change it. Changing the concentration will not change this one here, okay? Right now, here, I need to balance off the electrons here. Here's 6, here's 2. So times this all by 3. Say 3, 6 now. So I can cancel off these 6 electrons and this one here. Okay? So I put down this is called the over equation now. 3H2 gas plus is 1 more here, right? Now here's 6H plus. It's like bring over 40 minus 6 is 8H plus. Okay, to give me 2Cl3 plus here, plus now 7 H2O. That's not right. Okay, 14. 14, why? Because here is 6, here is 8, 14. So I just add up. Now I do not times 3 times 0 was 0. But if there's a value here, I don't times the value for the E naught. Okay, this is this answer. Okay, so this is called the overall equation or overall redox equation or reaction. Now, if I want to use this equation, okay. Okay, so standard cell potential. E reduction minus E oxidation. So who's undergoing reduction? This one here. I must quote the original value plus a sign, plus here, and plus 0. So same, see, I can do it by this way or this way, same. If you don't ask me for the overall equation, I don't have to do this way. I just do by this way. Okay, so this your, of course, you observe here becoming more and more green color, because this is green. This is your orange. Okay, both are inside there, but this one will have a higher concentration now. All right. Now, next, of course, is your purple color. This is a purple color. Remember your titration at purple color. This is your faint pink or almost colorless. Okay, Mn2 plus. Okay, so this is the reaction here. Of course, Mn is from manganese 7. Manganese 7. Okay, or manganate. Okay, manganate here. Okay, of course, it will give you MnO4 minus here, right? Now, here, of course, the whole thing is minus here. Okay, now this is minus 2. You see this X here is 1 here. So plus the 2 contribution here to give you minus 1. So 4 times minus 2 is minus 8. This X here. X minus 8 equals to minus 1. X equals to minus 7. So X minus 7. So this minus 7 here. Minus 7. So plus 7, what am I talking? Plus 7. Sorry, how can minus? Plus 7 must pass 5 electrons to become Mn2 plus now. Okay, right? That's why this must come from somebody. Who? So we put in hydrogen here. Remember, this is your standard electric potential. And of course, here is positive. This is positive here, the poles. This was negative. That means hydrogen again will be giving out electrons. That means hydrogen is undergoing oxidation. That means H2 becomes H plus. So this again, your negative pole. This is the equation. Okay, now, right? You go back and read again. Okay, I don't want to haggle too much always. Okay, so originally don't have 5 H2 gas becoming 2H plus and so forth. MnO4, same thing here. Don't have the 2-1. Okay, this part here. Yes, you just copy from here. Right, this is the equation. Yep, so this one here. Okay, so quote the E naught values is positive Y. It's positive Y because it's going forward. Right, if it's going forward, that means that this is positive. If going backwards, it's going to change it to negative. Okay, so this is how you work it out. So here, right, so I need to make here equals to the same number of electrons. This 5 here originally and this 2 here. So 10 is the common factor. So times this by 5, 5H2, 10H plus, and 10 here. I do not times this thing, okay? It's 0. Okay, now here, 2, this times 2 here, 2, I times this is 16, times here is 10. 2 Mn, and here, now here is positive 1.5. I don't times no. I leave it as if, because if I increase the constant, the amount, because it always must be 1.0 molar, okay? So I put 10 liters here or 1,000 liters here, the same, because the constant is the same. Okay, so I don't change this thing here. As long as it's standard, I don't change. Okay, so I can cancel off the 10 electrons here, and of course, it give me this. This is the overall ionic or overall redox equation. Okay, so this is the value. You can add up here. Right, here and here, or you can use this equation. Can so I've given you 2. A famous one, your purple color, of course, this purple color, as it goes on, purple color will be decolorized. Okay, this will be decolorized. This is your colorless. Okay, so if you continue operating in this system here, this fellow here, the concentration here will decrease. Purple will become colorless. Okay, as a cell progresses. Okay, so these are two different ions, 2 different valencies for the same element. I use platinum as my source of collecting and distributing electrons here. Okay, right? So now this is a famous one. This actually is called a fuel cell. You will see later we do batteries. Okay, fuel cell. This is used in rockets, because there's no waste. oxygen or hydrogen becomes water, which they can drink, and can use for washing, whatever, in space. So it's very recyclable, blah, blah. So now fuel cells, like here, right? They have got 2 rockets here or 2 things here. Okay, don't care about all this thing, okay? Just put platinum here, look at it. This is a caramel cell, doesn't matter, okay? Okay, now this is a voltmeter here. As long as the voltage tube here to contain, remember, you must always have the arrow going in, okay? Arrow going in. Okay, so there's hydrogen gas, 1 atmosphere, temperature equals to 25 centigrade. Here, pressure is 1 atmosphere again. Okay, now here, of course, I am putting it under acidic conditions. Okay, later you see one I got here is under alkaline conditions. Right now, here you see this here, put see, I just change, I cut and paste. Okay, alkaline conditions, same thing, which actually came out in another form in your exam question like this. See now, see, oxygen, hydrogen in alkaline. Okay, so don't care what they give you, as long as you know your basics, you'll be safe. Right, now let's go to here. All right, remember, now it's all gas, is non-metals, right, with the ions. Okay, ready? Okay, the first one here, I say the diagram shows laboratory illustration of a simple hydrogen oxygen fuel cell. You say in acidic conditions. Okay, of course they put down there, but sometimes you guys don't know how to read question problem again. Okay, acidic conditions, because this one here is what is in here. Is in what is in alkali, is in alkali conditions. Okay, so it's very important now, because the E naught you choose it will be different. Okay, now let's do here. All right, I show the whole question. Of course, there are other parts that I don't want to concern you with that. Okay, now this is the arrangement. Okay, you can draw it out, simple one like this. Of course, the simple one is like this. That simple one, right? Just put two contraptions here and here, and put this as 1 molar HCl equals our team already what? Okay, same thing. Okay, of course, this one would not be very accurate for a long time, because ions get mixed up together. In this one here, you separate them, you can get a more consistent and constant reading. Okay, that's the whole idea of the salt bridge. Okay, now mind. So I got oxygen gas here. Okay, all right, it's not ion, oxygen gas here, and the hydrogen gas here. So it's got fuel cells. They can burn with water and give electrons. Okay, so what happens here? So they found, oh, when you do this, the voltmeter got reading, that means they can produce electricity. Interesting, isn't it? Because they have an experiment. So what is happening? Who is undergoing reduction? Who is undergoing oxidation? Very simple. Okay, because they did it all before, and of course, you got this thing called your data booklet now. Okay, all here. So remember, the first thing, of course, is acidic solution. So the hydrogen electrode, where should I choose? Oh, so hydrogen is all copper, iron, F, blah blah blah, MnO, oh, where's hydrogen? I thought it's here. Here. Oh, sorry, here. I put a mark here. I put orange, green color. All right. See that? See that? See, hydrogen here, acidic here. Okay, so this is the, of course, standard hydrogen electric potential. Okay, right, 0. See, and this one is hydrogen. But in what alkali conditions? See, different. See, the choice of which one to choose from is very important. So I got to choose one here, because why? My conditions is that it is acidic. Okay, so anyway, that's quite simple. Now oxygen here. So I put down so I won't miss it. Sometimes I'm quite blind. See? Oxygen, okay. Acidic, yeah, baby here. Yeah. Right? Okay. Right. Now, so oxygen, there are 4. 1, 2, 3, 4. I must be careful. I must not choose hydrogen peroxide, because there's nothing that I was going to water. I cannot choose this filler here. This don't know what kind of substance it is. Okay, so these are the two here. Oxygen in acid solution and oxygen in what? Alkaline solution. Now this, remember, this one is you very famously use it in form 4, remember not? In like electrolysis. To go back, what's it meant? 4 OH minus. Okay, never mind. Now this is the one we use. Okay, for acid. Okay, let's see. Okay, so right here. Now, see, I cut and paste for you already. Okay, so remember, so now who is positive? First, of course, you must identify. The first thing is poles. First thing is poles. 2, okay, write the ionic equation. 3, the overall equation. Okay, equation. 4, better talk about here actually poles, and of course, it talk about the direction of electron flow. Direction of electron flow. Okay, and of course, last is the EMF of the cell. Okay, 4 things here. All right, now, so these are the 2 cells, half cells. So how to find the charge? The poles easy. Is positive here, it means here is negative. Very simple. Because everything is done in comparison. Okay, so of course, hydrogen here is negative. Is positive. That means negative means what? Electrons are coming out. Electron flow. That means what? What's happening here? Oxidation. Here's one go what? Accepting electrons? Reduction. Simple. Now, how, see, they ask you now, here, write half equation or half ionic equation for the reaction occurring in the left hand oxygen side. Left. See, when you face you, this is the left hand side. This is the left hand side. This is the right hand side. Because it's face you. Okay. So what's happening here? What's the equation? Of course, it's reduction in. So of course this one. See, but you must not write both. You must not write both. Salah tau. So O2. So it's O2 plus 2H plus copy this plus 4 electrons plus 4. So 4 electrons. Okay. One direction now to give you what? To give you 2H2. Balance. Fantastic. 4 hydrogen. Balance. State the polarity. Left hand. So simple. Just child's play, man. Positive. Okay. Use the data board to calculate the voltage of this cell. So simple. And there. Right now, you can just this one now. Okay, or you want to use, see, if it now asks you for the overall equation, you can just put E cell, right, equals to E what? Reduction minus E what? Oxidation. Very simple. Reduction is what? This one 0. Okay, so use the original plus 1.23 minus 0 6 plus 1.23. So here's right. Plus 1.23 volts. See whether I got it here or not. Okay, here. All right. See now. See? Mark. See now. One mark. See now. For E, positive pole. See? 1.23. Ignore the sign. So simple, man, I tell you. Once you understand the concept, is very simple, no problem. Okay. Okay. Now let's get other questions. Right now, this is for the choice of your fuel cells, oxygen and hydrogen in an acidic medium. Now here is a okay, blah blah blah. I won't go through here. Okay. Now here I put on here is for an alkali conditions because it came out here. Right now, it came out here, right in a different. But I like this like a. I think it's fantastic. I mean, I just changed this only one. Okay. Now, in alkaline conditions, if this is given to you, now how do you solve the whole problem again? Okay, very simple. Now the choice. I put down the choice for you. I'm going to go back here to show you how I got it. Okay. Remember in alkaline conditions. Okay, for acid, for H2, I told you, right? You cannot use anymore. Double A. Here, H2 with 2 OH minus now. Yeah. Okay. That means this is the one here. See, the voltage difference there. All right, never mind. Never mind, huh? So now minus 0.83. Now oxygen again. Why not? Oxygen here. I can't use that here because it's acid. I don't know, alkaline. So, okay. So plus 0.4. Got it? Okay. Right. Now let's go back to here now. So I cut and paste for you here. So easy lah. Okay. See that? Hydrogen with alkali. Okay. Minus 0.38. It's not 0.00 anymore. This what? This hydrogen. Oh, I salah ni. Okay. I cut and paste wrong. Sorry guys. I say I was hurrying. It's like hurry is terrible. Now mind, we click on here. Okay. Okay. It's plus 0.4. All right. I think I remember this. Okay. It'll be O2 is 4H2O, right? This famous one in your form 5 now, plus H2O here, plus I think it's 4 electrons. Okay. Sorry. It's OH minus. See, when you hurry, you mess. See, okay, 4 OH minus it. Let's see, 4. See, okay, now mine. Mohamdan 4 OH minus. Okay, go to here. Right, is 2. Right, and what is the value? See, now mine, so it learns it. Okay, 0.40 plus 0.40. Okay, it's tak boleh guna. Okay, so this one here. All right, so remember these are the two I got: oxygen and hydrogen, alkali conditions, now. So which is positive? So remember poles. First thing, of course, is the poles. Poles. Okay, poles. And one is poles. Who is positive, negative? Now remember hydrogen here is negative, so positive, obviously. So negative means it's negative. Very simple then, right? You decide from looking at the comparison. Okay, now. All right, so here now, what is the equation down here? That means, okay, 2, direction of electron flow. Okay, of course, flow from here. Negative is that source of electron. So here must be undergoing what? Oxidation. Here must be undergoing reduction. Yeah, simple, right? So you want to put the equation very simple. You'll be H2. Right, now copy the equation from here. Right, plus, plus 4 OH minus, plus 4, 2 or 4? 2, I mengong. 2. Okay, never mind. Sorry. 2 OH minus. Goes to, okay, one direction, boy, goes to what? 2H2O plus 2 electrons, okay? 2H2O plus 2 electrons, okay, now, see? Right? Okay, and now it's going backwards, it says plus 0.83. This is your E naught in volts, okay? So this is your negative pole. The positive pole is, okay, that means positive pole is still going this way. Okay, reduction here. Okay, so O2 plus 4 H2O, O2 plus 4 H2O plus 4 electrons to give you 4 OH minus. Yep. Right, right? 0. Positive. So going forward is 0. Plus 0.40. Okay, now let's make sure the electrons are done. Okay, let's put blue color. All right. So remember, here 2, here's 4, so I times. I don't time this. Okay, just times here times 2. So give me what? 2. Here's 4. Here's 4, and here's 4. So this will cancel off. Okay, so I put a line here. Right. Right. So this will cancel off now. Okay. Right. So this will cancel off. Interesting, all will cancel. So you actually get just water, no? That's why O2 and give you water, 2H2O. And the voltage is the same, is it? E cell is equals to, right? You add them up. This one you can add up. You know, this is the method to add up. So 1.23 volts positive. Now, if we do by the formula method, that's same, you know. E cell equals to E reduction minus E oxidation. Now, this E must be original, okay? So who is Gannon reduction? Is it not? Okay, no, plus electrons. So what's the original? Check here. Original is this one plus 0.4, okay? Plus 0.40 minus original. See, I cannot use one. That's why I changed. Why? Because I changed the direction. Here was original. Original is minus 0.83. Minus 0.83. That means it will give you the same value. Plus 0.83. You what? Plus 1.23 volts. See that? Same. Fantastic, isn't it? So you can derive the overall the E cell here by doing the whole thing and getting the equation, or you can use by this method. This is obviously the choice that most students, because it's very fast one. All you need to know which is the negative pole, which is the positive pole, and then you can decide. Okay, right? Same thing, All right. So remember, alkaline condition. This is called a fuel cell. The fuel cell, it means the voltage given by fuel cell is same 1.23, whether it's alkaline condition or acid condition. Interesting. Now this is a common one. Okay, now this is what given. Okay, although the standard electric potential are measured of solutions with a concentration on 1.0 volts, cells batteries tend to operate with more concentrated solution and blah blah blah. So now these are hydrogen oxygen fuel cells in dipping in annuation. Okay, under alkaline condition. Now this okay, right? So they tell you the directions. Okay, left hand. Okay, right. Anode means oxidation. Here is where they went wrong. Okay, anode always means oxidation, but here's reduction here. So don't care, even though they are whatever they say, Cambridge is always correct. Okay, normally most books say anode is always oxidation, cathode is always reduction. But here it's reduction. Okay, don't care. Right hand side. Okay, right hand side. Left hand side. In exams, you play the game according to what Cambridge say. You don't be too smart. Okay, they're always right. All right. So they ask you now. They give you this one here. See, remember in alkaline conditions, alkaline condition. See, O2 plus 2H2O, 4E, isn't it? 3, 4. You can see here. Look here. Okay. See that? Yeah. This one. Yeah. They only don't quote the value here. Okay. Okay. So they help you on this one. Never mind. Now, left hand side is a hydrogen. See now. H2 plus 2O minus. See 2O minus. Okay. Yeah. See here. Watch and learn. Yeah, wrong one. See here. 2H plus 2O minus. Yeah. Yes. Okay. So remember, H2 is on this side, isn't it? So what did they do? They put on the other side, right? They put it correctly, which means they tell you that this is going to be what? Negative pole. This one be positive pole. Right? As electrons means what? Reduction. Negative pole means oxidation. It means the source of electron. So they write it for you. So nice of them. Say what is taking place. Okay, so of course, in this case here, if you were to write the E values here, very simple. What is this one here? Going this direction, H2 plus O minus. Okay, H2, right? Plus O minus, right? Going this way, isn't it? I put red, almost time already. Right? It means it must be positive now. See, going this direction, okay? Going forward, it's minus. It's positive. Positive is 0.83. Okay, it's positive 0.83. Now here, O2 plus 1 going this way. O2. All right, O2. going this way. That means it's going here, positive 0.4. Okay, positive 0.4. This is the dead bullet to calculate EI say. So E cell is how much? E cell is, of course, E cell here is equals to 1.23 positive volts. Right, equation. So in this case here, you see overall here, right? Remember, I'll put red. So see, sometimes they ask you for overall. All right, so you times by 2. This 4, this 4, this 4, this 2. This 4, this one cancel off. So this one 4 cancel off. Okay, right now, this 2 cancel off this 2 here. Okay, so it's what? So it is H2 gas, put the states plus 2H2 gas plus O2 gas gives you what? 2H2O liquid. Yes! Full marks, man. Full marks. You see? Okay. Easy, easy. Okay. Right? Now here are some simple. Now here I want to go. See, earlier part I did SEP and SCP together. Now this is really SCP. Okay, I'm going to show you here. Now this one, of course, is your what is this? Daniel cell. I'm going to start with this one here. Okay. Right. So I got mix it all together, but never mind. Okay. Now here. Okay, we do more. Okay, now here is a Daniel cell. Right. Remember the Daniel cell. Daniel cell, if got 2 cells here without any hydrogen electrode, it's copper here. Right, remember, and here's a copper 2 sulfate. This concentration of CO2 plus here is equals to 1.00 moles per DM cube. See, it's a zinc here. And this here is a melt porous spot. I can put anything like, say, N2 plus here is equals to what? 1.00 mole per DM cube. Okay, so forth. So I now connect this part to a voltmeter here. Okay, guess who be negative, who is positive? Okay, now here you can see the whole thing here. Put different things here. Wow, very simple. Look at your data booklet again. Okay, for zinc and copper, zinc. Remember, this all reduction, reduction going forward is minus 0. Something here. Now copper is minus. Now copper is what? Okay, you can see for yourself, copper. Copper and 2 plus 1 is what? Positive, isn't it? So positive means copper is positive and zinc is negative because you compare all the hydrogen ones. Go and think about it, okay? So compare hydrogen, which means in this case here, okay, copper is positive, zinc is negative. Just like here, see now. Okay? Copper positive, zinc is negative. So you decided the poles already done. Now how about direction of current? Of course, here to here, okay, negative, isn't it? So what is happening here? So that means whose electron release must be zinc, isn't it? So zinc, look here, right? So zinc must be going where? Must be undergoing oxidation, must be going backwards now. So zinc is becoming Zn2 plus. That means the zinc is dissolving, equals plus 2 electrons. So in this case, the E naught here, when I put reverse, I must change the sign. Positive 0.76 now. Okay, this is a negative pole. Now, positive pole. Copper is undergoing reduction. Okay, which is this one here. Right, copper. See now. Okay. Let me correct. It's just one here. So it's same direction, so positive 0.34. Okay. So copper here. So copper 2 plus here equals AQ plus 2 electrons to give you copper. Sorry, here is positive 0.34. Fantastic. So that's an overall equation, right? 2 electrons here cancel off, so no have to times anything. So zinc solid plus copper 2 plus equals to give you zinc 2 plus equals plus what? Copper 2 plus equals, and what's the E cell? Just add them up, okay? Positive, the famous 1.10 volts. Now, if you use the equation E cell equals to, remember, E reduction minus E oxidation. I didn't tell you the right and left now. This is better. So who's undergoing reduction? Okay, copper. So I use the original one, plus 0.34. Who is undergoing oxidation? Zinc. I must use the original one, not the change one. So it's minus 0.76. Again, plus 0.34 plus 0.76. Same reading, 1.10 volt positive. See, simple. Yes, not. So now you learn how to write the SCP for every cell you want. Now we will continue this. Here I give you all the choices. This famous equation. Of course, I think to me this is the best one now, because you can easily decide which oxidation again. But right and left itself is don't wish which one now. Cathode and also don't wish cathode. Okay. Now we'll go to more of these things, the uses of E0 values here the next time I meet you. Okay. So I think I will stop here. Right. So please go over it. Just go over it, and if you